Ladies and gentlemen, welcome back to our online summit. We've just arrived at the networking lounge. It's the fifth day of our online summit, and today we're looking at the topic 3D measurement technology. This is actually huge, and you can ask questions, give us input, and we'll pass those questions on to our experts on stage. Just use the live chat button on the lower right side, and I'm happy that these experts are with me. We'll have Adrian Kryschok, Thomas Domaschke, and Michael Kleinkes. Maybe you just give us a short introduction of yourself and your company. We'll start with Adrian. Just go around.
Okay, yes, hello. My name is Adrian Kryschok. I'm the CEO of the Spark6D company. We are part of the Pepperl+Fuchs group since 2 or 3 years. And what are we doing? We go to the customers, we measure robot cells, we try to digitalize robot cells, and we do some software developments.
Thanks, Thomas.
Hello, thanks for the invitation. My name is Thomas Domaschke. I am the managing director of the 3D Aero. Before I got into this position, I was research assistant at the Institute for Aircraft Production Technology at the Technical University in Hamburg. And we had a shared research project together with the VMT. And this research project was the founding motivation for the 3D Aero, actually, because at the 3D Aero, we are developing automation solutions for the aircraft production and maintenance industry. Smart solutions with industrial robot applications, as well as mobile devices, mobile inspection devices.
Thanks. Yeah, we got almost a good impression by the live launch presentation from Michael. Maybe just a short introduction of yourself.
Hi, happy to be here. My name is Michael Kleinkes. I'm the technical director of VMT. VMT is creating turnkey solutions in the automotive industry and in the medical pharma industry. We are specialized in giving the robot eyes. So we are the ones who are doing the process automation, doing the solutions. My background is robots. I studied together with Adrian, so we know since many years. I know Thomas since many years, and I'm coming from the side of doing process applications on the point clouds and on the 3D measurements to create a turnkey solution in the industrial environment. Less research-based, more it has to work every day, 100% based.
Thanks, gentlemen. And we now want to go into detail. We already got a good impression of the technologies. There are different technologies in Michael's presentation, but maybe just give us a little glimpse of it. Where do they differ? What is special about the 3 technologies you cover?
Sensor technologies differ as much as the application they were developed for. So there are very different characteristics. They differ in their field of view, they differ in their measurement range, they differ in the robustness on different surfaces, of course in the measurement principle. Maybe a short example, if you compare the white light interferometry, very complicated term. You can measure in the micrometer scale with the micrometer resolution, but with a really tiny field of view. If you want to find defects, very small defects, which are very common in the aircraft industries. And compared to a LiDAR technology, which we already heard this week about, where we measure long distances, large volumes, and up to 50, 60 meters if you want to get an impression of the surrounding space. Yeah, and but these are just a small set of characteristics where sensor technologies differs. It's always a matter of the application, what you're looking at.
What type of application can be solved with these technologies?
Exactly, I think it's exactly as Thomas said, it depends on the application. For us, if we want to digitalize robot cells, we use very often laser-based measuring systems because we need a high accuracy for long distance, and this is why we're going to to use this technology for that application.
And in contrast to that, in the aircraft industries, as I already mentioned, we are looking at really tiny cracks, defects on shiny surfaces. So with, from an optical sensor perspective, really difficult surface conditions. And there you have to take also different technology. And we are using this white line interferometry which acquires really robustly data even on shiny surfaces.
Actually, which sensor you're using is one of the basic knowledge that you need to solve a problem.
Yeah.
So if we do projects for our customers and we come to a point that we say, okay, this is the one sensor technology solving a problem, that is a sensor. There's a story. We had a project and we searched a sensor and everything was fine. That was a technology projecting on the part and the problem was not solved 100%. And we changed in the same technology, the same manufacturer of sensor, just to another model. So the projector had more light and the density of the point cloud was different, and due to the reflection on the part, with a new projector with more light, it was a completely different story. In my eyes, the usage of the sensor, the knowledge and the experience, which sensor is solving the problem and which measurement technology is adapting perfectly to the problem that you have on hand, is a key fact that you need to solve and the key competence that you need to deliver. You can't solve a problem just by picking a sensor or making a rough estimation. LiDAR is right. You need it in the perfect setup. And I think this competence is one of the key points.
Yeah.
How do the sensors differ? I mean, measuring, for example, a building like this needs another sensor than measuring those cards or whatever, and then finding cracks and stuff like that on this.
It's not only the principle we are looking at. Often the application also has a challenge regarding the size of the sensor or the weight. We often, or we commonly attach sensors to robots. So we give the robot eyes, and there it's always a really critical matter of fact how big the sensor is. So you not only have to look at the application surrounding or the application characteristics, you also have to take a look at the tool you are using or what you can, the setup you're choosing.
And we are ignoring one element, that is price.
Price
so
as well.
Most of the customers say, give me a sensor which is light and small and which costs nearly nothing.
Well, you pay for it.
You pay for it. And the system, the approach that we use at P&F in the family, and we are all bleeding green, and we want to sell our sensors because they are great, and we wear green socks because we are green. And the first approach is there a portfolio sensor of P&F solving the problem? Yes or no? If the sensor of P&F is not the very best choice for the customer, we go to a different one. Maybe we buy a sensor from a competitor to solve the problem. At least we at VMT do it like that. To be at the end, at the customer value and say, dear customer, that is the sensor. It is slightly bigger than you want to have it on the robot, but this is the price and that is the one you need. If you buy a cheaper one, you won't solve the problem. A more expensive one is overshooting. So that is always a compromise that we play against sensor price, size, and portfolio external.
And one thing, I think just the time, because if we are looking to the production, we don't have so much time for getting data. So it means we need sensor that it's working very fast. But we need accuracy with the sensor. I think it's another point that we have, it's very important for this.
And in our company, in P&F, we even sometimes take one further step. So if we don't have a sensor in our portfolio and we don't find a competitor who is actually having one in his portfolio, then we even take that further step and think about developing a sensor or optimize a sensor, because we at P&F have also the capabilities to come up with other sensors or to optimize a certain sensor from our portfolio. And the 3D Arrow is more research and more into research and into development heavy projects, and it's happening quite often that we develop a sensor for the application because it's often really complex problem statements.
And I think it's not only the hardware side. I think it's very important the software side, because you can take one sensor and if you develop new algorithm, you can solve totally different problems with that.
That is actually great. VMT is now 25 years old, and half of the time we were independent. We didn't knew Pepperl+Fuchs as a mother. Now we're part of them, and you say a great part. There's a sensor, we need it, and it's not exactly what we need today. So we talk to Pepperl+Fuchs, and they make it. They make us a sensor. The software is coming in-house, and there comes a new feature. We need something else, and we go to a department. It's on the third floor here. We just go there. We go to Christian and Christoph, and they make it. And try that with a sensor that you buy on the market. Try to go into the third floor to Christoph and Christian and ask them to change a bit in the software. Well, they won't do it. And that is a crazy good advantage that we have. We can do the projects, and Pepperl+Fuchs is providing us with the tools that we need. And that's great.
And I think this is a really, really important thing. If you look at metrology applications or inspection solutions, you have to be really flexible, because you are looking at a really, really broad spectrum of problem statements. So you have to have a really, really big flexibility. And I think this is one of the things which is really, I don't know, really the best or one of the greatest things P&F can deliver, the flexibility in that company. Speaking
of flexibility, let's have a look at your maybe daily business. We got the example of the combustion chamber, for example, in the presentation from Michael. So you've got this huge thing. How big is it? 3 meters?
Actually not
like that?
So huge, but compared to the field of view, what we are using for inspect, that think it's really, really huge, because the field of view of that white light interferometer, which I already mentioned, is just a few millimeters, has just a few millimeters measuring volume. And then you have that combustion chamber, which can like get a size of, I don't know, 1 meter, 1.20 in diameter. And this means if you want to inspect the whole surface of that workpiece, you have to take around 75,000 single images. And then, if you have that tiny field of view, you have to be certain that you hit the surface with the image, that you are not acquiring air. That's not really interesting, or that you've mounted it on a robot and you don't want to crash into that workpiece. So you have to be really flexible. You have to know where exactly the workpiece is and how the condition of the workpiece is. So we've, after, I don't know, 60,000 operating hours within an aircraft engine, maybe in the worst case over desert, then such a combustion chamber can have holes the size of a finger, or it maybe
sounds scary.
Exactly, who is flying every day. That might sound scary, but it's the technology is so robust that it even can take such hole in a combustion chamber. But we have to adapt to these conditions, and therefore flexibility is the key point. And if you look into automation, flexibility, we all know flexibility is the main challenge, because normally you have to have a really well-known setup. You have to know the boundaries. You have to know the framework in which you develop an automation application. And if this setup may vary, then it gets challenging with automation.
Okay, so today we've got the combustion chamber that has to be inspected, and then the company calls and says, okay, tomorrow I'd like to have this or that part inspected. What are the next processes then?
Yeah, this is really challenging to change a process from one workpiece to another workpiece. But it's like, then it really gets, a system gets really profitable if you can use it for different workpieces. And so the flexibility is one of the, yeah, I think, as I already said, it's a key factor, and for the customer, it's the main profit is in the flexibility of an automation system. Or, of course, in the stability. I think from my side, from the aircraft maintenance side, it's the flexibility which counts the most, and on your side, which on the automobile side, it's robustness.
It's robustness and working all the day. So there's a good example. We built a system at Volkswagen, and it's a bin picking system. And if this system is running out of parts, then someone has to come and open the door and get this stocked system running again. And we call that the number of people with white shirts is increasing. So there's the one with the blue trousers, and he makes that running, and then the line stops. The first with the white shirts comes, and then 30 seconds later, a second, a third, a fourth, a fifth. If the number of white shirts people increase at a production line, then you are in trouble. So there's our major.
That's normal life when white shirts are.
White shirts are. And yeah, that is the topic. And what we do at VMT to increase the flexibility and to use the systems is we have a frame software where you have your part integrated, and we provide our customers the knowledge that they can use our software without programming it, just reconfiguring it to create a new setup for a new part. That is limited, for sure. If you are inspecting glasses or combustion engines, that is the difference. But if you are glasses and maybe cups, that can be integrated by the customer. And that is a very important part of our business, knowledge transfer. We deliver a solution at VMT to our customers, and then we enable our customers that they can use their machine. It's not anymore ours. They bought it. Their machine to do different tasks by their own and really easily create the flexibility that they can use with it, and to still hold the stability and the productivity of the system to avoid the white shirts.
But this shows, sorry.
Yeah, okay. There may be one point, what do we understand under flexibility in this path? It's a totally different application, because, for example, now in the summertime, if we go to the customer, we have only 2 or 3 days for all measurements, to finish the measurements. Because what do? We have to calibrate cameras, for example, VMT cameras. We have to calibrate some robots. We have to calculate all transformations, give it to the robot programmers, because they want to finish their job. And so it means flexibility. It means we have to go on site. We cannot work in the office. We have to go there, bring our mobile measuring system, and do the job there.
I'd like to come to that point shortly. But first, Thomas, you wanted to add something?
Yeah, I just wanted to add that the extract of that, what we said, is that metrology is really important for if you want to do automation, because only by 3D measurement sensors you bring flexibility into automation. You bring perception and you bring eyes into the system. And then the system is able to adapt to changing surroundings. So this is the flexibility. Metrology brings flexibility to automation. Yeah.
Eyes that are needed, for example, to build up a digital twin. Michael gave us a view of that. You did this for a production line in the automobile industry. Tell us more about that.
Okay. So why are we doing this, or what are the reasons for creating digital twins? Of course, there are a lot of important things, but maybe we can think about one thing. The problem is the time on site is very short. It means there are a lot of things that should be done, programming, in commissioning, something like that. So it means if you can prepare a lot of work before you go on site, before you start with building the robot cell, that's of course very, very good. It means we can go there, we can create a digital twin as model, give it to you, let's say some months before, and you can start everything. You can do some programmings, you can do some testing, everything before you go on site.
Mm-hmm.
I remember when we both started measuring, that is, I don't know, 15 or 20 years ago.
Yeah,
I don't know. We were students and we went there and we trained all that in the lab. and it needed 2 weeks to measure a robot and a cell and everything. And then somebody came and said, you do that now at the weekend in 10 hours. And that is a development on the market that we see, and VMT is special. The time that you have to change your production is decreasing nowadays rapidly. So an OEM manufacturer of cars, for example, he had 10 years ago a week to change his production facility. Today he has a weekend to do that.
Yeah.
And that means your preparation is completely different. You focus on the parts that you have to do manually on site, and you try to simulate everything. And the digitalization is a step into getting a picture of the reality to the computer, to the office, to a very moment where you are relaxed before you have enough time to prepare everything. But the moment when you're on site, it has to be ready. You only go there, you flash up the firmware, and then you make the checks and you go again.
Yeah.
And that is a huge step, and 3D measurement is pushing that.
In how far is metrology important for digitalization and the steps towards the future?
It's actually the key element. So it's like the bridge between the physical world, the physical industry world, and the virtual world. To receive a digital twin, you have to use sensors to acquire the data, at least once. So maybe you have models of your robots, your work pieces, but then the actual processes are so narrowly tolerated that you need the physical image of your physical workpiece to bring it into the virtual world, to take your processes, to plan your processes,
Yeah.
to set up your processes, to commission your processes. You need all the information, and metrology is the bridge between these two worlds, actually. So it's a very important. It's very important nowadays, and it's get more and more important over time, because computational power is increasing. So we can do more and more, and in the future it will even be more. It will get more important with time.
Yeah, I think so. There are 2 steps. The first step is go on site, get the current situation, bring it from the real world into the virtual world. Then you can do some simulations preparing everything, and then you can just take the results and bring it back from the virtual world to the real world in a very, very short time.
I can imagine that the past 4 months had a big impact on this, and thinking about that, COVID-19 as a driver for this, or non-contact metrology.
Yeah, non-contact metrology is the step in the future. When you go to an object and you touch it, you always kind of modify it. Even if it's a micro touch, you touched it. And what you want to do is you want a safety distance, you want a fast measurement, and you want to digitize as much as you can. And in times of COVID, more simulation, more virtualization is better, because like we do it with the conferencing. Some months ago, for every meeting, we met in a room, we sat together and we talked. Today, we do WebExing and whatever conferencing tool we are using, and we try to avoid personal contact, right? Going back to a good level, what is needed, what not. The same for measurement. Avoid the personal contact with the object. So try to simulate it. Try to measure it and virtualize it to create a digital twin of the reality back into the simulation, and try to virtualize every object. What we do nowadays, in many cases, is we have one. We have the one object, but we produce 1,000 of it every day. And what we want to do is all these thousands of every day create it as a digital twin and save it. Look at them later if we run into trouble. Pull number 517 out of the database and see what was that. And what we do today is mostly we have one CAD, one simulation, and then we produce the parts. But the future will be the digital copy of every single produced element to make statistics, predictive maintenance, or even risk aversion by saying 517, everything was okay. Put back.
Quality management.
Yes.
Yeah. Just a short example. If you go back to that combustion chamber, this combustion chamber will get another check. And then you don't start at 0. You take the digital image from the last process, look at it, look where you had the cracks, the defects, the anomalies, and then you just open up these defects, and you can use this data to also improve your processes. You can also improve your workpieces, your design for special workpieces. Then you see where are the weaknesses over time. So you have the whole workpiece's history. And you can predict, as Michael already said, you can predict the future of that workpiece, of that material. Adrian just told me before that panel talk that he just measured, that he just the first time get to the border of 10 billion points at for a scan of a...
I just try to imagine.
Yeah. And then get back to that contact approach. So you do 10 billion contacts.
Yeah.
This would maybe be, you would not have the time to do these 10 billion contacts. And 10 billion is a really impressive number.
Yeah. And how far? Give us a picture of that.
Yeah, okay. In this case, when we get 10 billion of points, you can imagine it's not only a robot cell, but the production hall. It means we are talking about, let's say, 100 meter to another 100 meters, something like in this size. But the very interesting thing, we only need 2 days to get this data. So it means there are, of course, a lot of positions where we do the scans. But at the end, after 1 weekend, we have all the data, and then we can start with the post-processing things with that.
How long does that take? We talked about that briefly in our live launch, processing the data. I mean, this is a huge amount.
Yeah, exactly. It depends, of course, of the application. If there are a lot of things where we have to be sure that we can see everything or not, of course. But let's say we need maybe 2-3 days after the measurements that we can prepare everything to put it together. It's a very important thing. Because the first step is just to get the data. The second thing is to bring it together. It means to get it in one coordinate system. So it means we need for that 3-4 days.
Yeah, bringing it together. It's a good point for Pepperl+. You mentioned in your presentation. Tell us a little more about that again.
Pepperl+ is a great idea. Pepperl+ is the idea how to create more value out of something. So taking a point in space and a point cloud, and what can we do with that point? What can we attach an information to this point to create more? And the easiest way of Pepperl+ is the color. So that's very obvious, a color attachment to a pixel. But taking an example, we had a fridge, and the backside of the fridge, there's a copper line that had to be inspected for a reason. And
whatever it was.
And the robot had to go along this copper tube, and this tube was shaped in an arbitrary form. And with a 3D point cloud, we weren't really able to extract the copper tube. With a color picture, we weren't really able to see the copper and the background that was not really distinguishable. So again, consulting, what is the right sensor, what not. And at the end, my colleague Mark, he took the hairdryer of his wife, and he heated up the fridge backside with a hairdryer, and he took a thermal camera, and he came to me and said, look at that. And copper is a very fast thermal element. And the backside of the fridge and all the other elements, they were kind of slow with the temperature. So he heated everything up. And then he took the AR infrared picture of the scenery. Bam! There was a tube. And so we took the 3D point cloud. We took the infrared measurement. And so there's the Pepperl+ idea again. Temperature and pixel. And then you have a point cloud temperature map. Ah, that was so great. And then it's easy to work with that. And that is a Pepperl+ idea. And in the future, we will attach much more.
Yeah.
And maybe smell.
Yeah, for example, a smelly cloud. Well,
Yeah.
no pictures at all. But what, for example, what might you be thinking of?
Yeah, actually, a smelling point cloud is more artificial right now. But if you talk about temperature, it's really about searching objects in point clouds, and that is where Pepperl+ technology comes into play. For example, taking a medical application where you have transplanted skin on your arm, and you have to test these transplanted skin, and you can use the technology to see how the skin is reacting. Or in Formula One, you can see how the color flow on parts is moving when you do wind channel tests. And they are crazy ideas, and that is exactly what we do. Pepperl+Fuchs is expanding its business by new ideas, new business development, and our duty is to find these chances on the market where our technology adapts perfectly to some problems, grab it and extend it and go into this market and create value for our customers.
In automation, we often try to copy the capabilities of a human being, and it's 3D sense is not enough. So just seeing a point is not sufficient. If you add up color or contrast into that point, suddenly you get the same information as a human get. So as an example, you're looking for cracks on the surface. Then you take the 3D point cloud, and then you have to find exactly the hill or the wave a crack creates on the surface. So we have to get data from the inner part of the crack. 3D. There has to be a point. So if it's very narrow, then in many cases you don't receive data from the inside of the crack. But if you attach an additional color camera, so get into Pepperl+, then you also are able to see shadows, as example, or to see the certain characteristics of a burning or something. Before it cracks, it burns. So there's a certain color around that crack. So you get additional information, and the human being is really good in seeing these cracks. And we always asked us, why does that human see the crack and we don't see it, even if we have that high resolution? But then we realized there's always something happening in the contrast. If you look from one side or the other, then there's a shadow or something, and the shadow expands that crack immensely. And then we don't only have to look at that crack, we also can look at the shadow. And this is also the thinking behind Pepperl+, which is really one step ahead.
And you said the system compares to the optimum of this object, or the picture, or the cloud, the pixel cloud, which was taken from the object
After.
before and after then.
Yeah, you can. This is one possible approach, comparing a perfect CAD model to the image you acquired of that model, and just take the difference, and the difference is often an anomaly. But this is just one possible approach. We often only have the data we acquire from the surface, and only work on that 3D data. And it's not. We have to be cautious, because 3D point cloud is actually, you don't have a surface. You have just points in a room which are not really related to each other. So you don't have a surface. So first of all, you have to bring the points into relation to each other, and then you can start to apply your algorithms.
Yeah, maybe one point just
Sure.
for others. As Thomas already said, additional information. In our case, we have some deviations and differences in the points. It means if we have a point cloud, for example, we measure the robot, we move to some points, we measure the points, and as reference, we get some points from the robot program. And then you can compare the points to each other, and you can really see the deviations. And this information, what is it? Is it the accuracy of the robot? You can use it for documentations, you can do the processes. The processes can be better then. And the last step is, if you have points, you can use 2-point clouds to get totally different information. In our case, we get not only points, we get transformation. It means you have rotations there. What does it mean? It means, how can I move from my point to another point? Can I go there directly, or do I have to do a turn? Something like this. So there are a lot of possibilities.
Yeah. Speaking of use cases, is a good keyword for a question from our chat. And since, well, the meat industry was discussed in the recent days in Germany, this is a quite good question. Can this technology be used in meat industry, let's say, to check the quality of meat grading, finding small pieces of bones, etc.?
That's a very, very interesting question, because meat industry means there are objects which are all very different. Looking like the same animal, but each animal is different. So it comes to artificial intelligence and flexibility and the combination of creating a robust system which is finding elements which a human being would find. So we come to a point where human beings stand there and looking at let's say a pig, half pig, whatever, and saying there is something there and that is bad because I learned it over the last years. And yeah, this technology can be used for scanning the animal and taking a picture of it and learn in an artificial intelligence in the picture what is good, what is bad. This is a process which has to develop, but at the end you can take a picture and say that part there that was never there, it looks bad, I don't know it, I mark it. Or that bone is always that bone, but it can be a little bit different because that is animal A, that is animal B or C, so it varies, but it is the same anatomy of the animal, it will always be that bone. Trained in, look at that, it's fine. And so this technology can be used, yes, in terms of creating an artificial network and deep learning and machine learning of these objects to see and to distinguish between good and bad or separate good from bad.
So there are two aspects. The first aspect is, of course, the acquiring the data. So with Pepperl+, we can get the structure or the geometry of the meat, and then with Pepperl+, we also get the color information of that certain point in space. But then there's this data processing as well and artificial intelligence, because the bone is not always, again, coming back to automation, there we would need the piece of meat to look exactly the same all the time, but this is definitely not the case. So we have to find the bone, and for a human being it's really easy. We know how a bone looks, and bones are really looking the same if it's a cow or if it's a sheep. But taking the normal approach, a rule-based approach, so you tell them a bone has that size, has that radius, often has this color, then it's a bone, is not the real approach. So I agree that artificial intelligence is the best approach. You train them, you show an artificial intelligence network 100,000 bones, and then it will be trained and will themselves find the bones.
Speaking of AI, which role will it play in the development of this technologies?
It will play a key role in the future. It is a development that we see that is huge. But on a process stability point today, we say it is also a technology that you should use with care, because AI means learning by failure. And if you build a machine which is producing parts, you want to avoid failure.
Or, for example, when you're maintaining combustion chamber.
For example, we to sit in an airplane, we don't want to make him failures with a brake detection, right?
If someone asks me, did you find that defect? And I tell them, with the probability of this will be not sufficient. So, yeah.
Yeah, and this failure is a good point. But artificial intelligence in the last years developed magnificent. And the possibilities that we have in the future is closing the gap that we today have between humans and technology. So artificial intelligence brings us more to Skynet, more to the situation that machines can decide. The question is, where do we stop, and when do we want the machine to decide and not to function? In many applications that we have, we want the machine to function. And if it doesn't function, we want to analyze why it didn't function. Artificial intelligence is deciding. Why did you decide that? Network. Bad. If you have to explain to the white shirt guys why the artificial intelligence crapped 300 cars at Volkswagen, that is not a good point to be. And we have to balance out the opportunities that artificial intelligence is bringing us for the future and to keep an eye on working machines and reliability.
We have to find the fitting application for artificial intelligence. So in the case of a combustion chamber inspection, you may classify defects with artificial intelligence. They tell you this is a crack, this finding is a crack, this finding is a burning, this finding is a hole. But the defect detection should still be done with usual data processing algorithms, where you can tell them if a defect isn't found, then you go into the code and you look exactly in your decision tree, yeah, because it has not this length and it has 4 arms instead of 3 arms, therefore it's not a crack by definition. But it's still a matter of research or issue for research to see why artificial intelligence decided something. But I think, to be honest, if you ask a worker, in most of the cases, why do you think this is a crack? He also will tell you, because I know how a crack looks.
Mm.
So, but we don't want to have it in our machines, because then it gets more like Skynet. But it's a really narrow, it's still a really narrow corridor where you can use artificial intelligence, and you have to be you have to set up boundaries again. The surrounding conditions have to be really stable to use artificial intelligence. Sounds strange, but in a way, if you train something to a net, it will find the features you have trained it with. And if the features are varying, so if you train it with bones and you show him a car, then it will get a problem with that car. Yeah.
At the end, I think today, if we would like to use this technology, it's very important that we know the problem. If we know the problem and if we are able to describe very precisely what do we have to do, I think that's a perfect technology, because then everything is known. At the end, it can be very fast. We get the solution. We have a big data where we can just take a look what was done yesterday with that. But the problem is, if we have a task where we don't really know what do we have to do, as we said before, I think that's a problem. So we need a lot of things that should be done in the future.
Mm. Speaking of control by humans, for example, or you, Michael, you spoke about Skynet. You mean like Terminator? And I'm just thinking a step before the T1000 on the production line. I think there are many concerns of humans, workers. What about their jobs in the industry process, in the production areas, and so on? What's your opinion?
It is an balance between where do you need a human being for decision, because experience is key. You have a process and it's packed full of experience. You develop a car, you build cars since 100 years, you know how to build cars, and that is, you know how to, is experience. On the other hand, we have a phrase that we use at VMT: the quality of human inspection is depending on the spiciness of the food the day before. And that is exactly the element. So the varying quality of inspection of a human being is not really wished. So a system which is objectively scanning an object and creating results, which are 24/7, 365 days a year, the same, is very nice. I have a good example. We deliver systems for measuring car quality, and this system spit out some numbers about the car quality of parts: 0.5, 0.4, 0.7. And there was a deviation of this accuracy about a range of 0.1 millimeters. And the customer said, that's bad. 0.1 millimeters deviation, that's bad. And at the end, after some minutes of discussion, I said, okay, let's make a test. Bring 5 of your guys that are measuring the car and measure it and write the numbers down on the paper. What happened? That was a deviation of 0.5. And after that, he saw, oh my God, the humans are creating a fluctuation of accuracy of 0.5, the machine 0.1. Stopped, acknowledged, system great. And that is exactly the way. So the humans are needed for high intelligent tasks, but not for repetitive, objectively judging elements. That is a task which is stupid for a human being. We need the creative ones, the constructive ones, and our brain capacity is much more than controlling parts.
We will identify the car even if we only trained on bones. So it's like these technology should be complemented with automation, and the discussion if automation is taking away the human being is as old as automation is. And I think it's on that way to the point we are right now. It always has been that it has been complemented. We give tools to the human being, not a tool which he has to take into hand and go to maybe an airplane, but it's like even a tool where he has a machine which is fulfilling a task which he has done before because it was a really redundant task. And but in many cases we are really dependent also on the worker, and this tool is actually takeable in the hand, so you can take it and go to the airplane. And then we, if you would automate this process so far that you would that the tool would go the way by itself, then you would invest 90% in the task to bring that tool to your actual workpiece, and this is not really profitable. So you take the human, he knows what to do, he knows where the place is where the defect is to be expected. He has experience, he knows exactly how to, if there's something in the way, he can just disassemble it. This would be a huge task if you just would add it in an automation task. So we complement each other. So we give that inspection tool to the worker, he prepares everything. We only have to care about the 10%, can invest 100% of our effort in these 10% and deliver a great system. So the human being is still, in my case, in the 3D Aero case, it's really important. It's not. I really like the discussion because in that discussion I can really underline how important the human being today is in an industrial process. But this may, of course, vary.
Maybe in a robotics, we have the same situation. I think, of course, what does automation mean? It means that we can automate. We can use a lot of processes and we can do them automatically. But on the other side, you need a lot of people. They can handle this. They can program this. They can simulate this. And I think automation, it means transformation of experience, of competence to another group of people. And as Thomas said, it will be very important that we have really good people there. They can work with that. They can handle the systems.
And it's not like, we come up with an idea today and we deliver a system tomorrow. Then it's maybe the flexibility of the system is not too big, and it's maybe something from the shelf. As example, this auto-inspect system, which we saw in your presentation, we began with the development in 2010, and we finished it in 2019. So there were like 9 years preparation to see how we can also adapt the running processes and bring in qualification for the personnel, motivate them, get an acceptance. So it's not from yesterday to today that we integrate, throw it over the fence, and then we start, and you can go away. It's a process. It's like getting these lines together. I think this is more or less it's a question of integration. So and acceptance. So I think.
And a very important task that we shouldn't forget is troubleshooting. Human beings doing stuff in the production is one part that you can maybe do with a machine, but the machine does it as long it does it. And at the very moment something happens, which is life, then troubleshooting is the very element that we are, even in the future, will have a hard job to integrate that into a machine. Troubleshooting is an ability of a human being which is excellent, and that is very hard to copy.
Abstract thinking.
Intelligence.
Yes.
Reaction.
Yes.
Yeah.
Creativity.
Yeah.
In troubleshooting, you have to be really creative to find a bug.
Yeah.
So you need that creativity, intelligence. So the T1000 I think it's pretty long way.
Bad or good?
Yeah.
One of those. But maybe a tool for humans in all these processes is virtual reality. We got a short impression with that production line Michael showed us in his presentation. What do we think about that?
Oh, I think virtual reality is very helpful for industry. In this situation today, when it's not so easy to go on site to work there because we know why. So it means it's very good if we can create the model and we can bring it to the virtual reality. And I think very interesting thing is that you can, a lot of people from all over the world can work in the same time, exactly in the same production cell. It means they can do some simulations, programming, everything. And then at the end, they can bring all the results together and put it on site. I think it's a very good tool for the future in the industry.
Working in a digital twin.
Yeah.
Yeah.
So you have the digital twin and you can cooperatively work in it. So again, a small example from the aircraft industry. You have these really experienced inspectors, which are really working on that issue for 10th of years. And they have to fly around in the world to inspect their parts they are responsible for. And in the future, with virtual reality, they can just be in a digital twin, which all the advantages, of course, also disadvantages, but there are many more advantages, and they can work on the digital twin of that workpiece and tell them, take a look there, and do their job from home, basically.
Another part that we see is globalization. So a manufacturer of, for example, a car in Germany today, he has the task that the quality of the car has to be the same all over the world, in Brazil, in the US, and in China. And we start to import cars produced in China, German cars. And the task is you have in virtual reality of your different sites all over the world, and you can control them by seeing them in one central place. In your office in Brazil or in Germany, you can see every single production line all over the world. You don't have to fly there. And then you can create a level of quality of production even in varying countries all over the world. And that is a great advantage, because what is the final purpose? Your product should be as good as possible and at the same constant quality level. But you want to produce it in the US and in China because the globe is big and you have to serve different areas of the world. And virtualization is a step in that direction, globalization, and keeping everything on your fingertips.
And if we think about some steps before, if we would like to create new production cells, something like this, the same example, we can do it with all the people all over the world. It means we use WebEx or another tools, but in addition, if we just take a 3D glasses and all the people are going inside of this cell, let's say just in simulated cell, then you can prepare everything. You can find some errors before you build it up. So it means it's very good to do it before, just in the virtual world, before we start with going machines and bring something on site.
It's a huge field. I'm also a little running out of time right now, but still want to take the time because it's a huge field. I think we haven't covered several aspects which might be very important for you. So just feel free if we haven't covered an aspect. What's important to mention?
Important to mention is that we will come to a point that technology will overtake the humans. That is a drastically statement, I know, and I narrow it down to certain aspects. So if we focus on an application, we start to be able to be better than the humans for this single task. And that is a development that we see nowadays. So we were building machines in the past, and now we are building intelligent devices. and using networks, globalization, Internet of Things, we are today able to make a huge step to create systems which are better than humans. And that is for me, in a technical point, a very interesting topic to go, to keep the balance, but to use these functionalities and technology that we have to overtake the humans. That's, be honest, a crazy thought.
Mm.
But we have to, of course, break it down to 3D metrology. So
In
this
this
means
moment.
that we are, the systems we are building no longer only have a functionality which is better than the human eye, but it also has the intelligence after the eye. So you can do all this data processing, experience-based data processing on the data you're acquiring with that sensor. So maybe this is the part where we can estimate that we will overtake the human.
Yeah.
And maybe one thing, as Michael already said, we have to develop some sensors, machines, and hardware components, but these hardware components are smart, so it means there are some algorithms running on this hardware part. And with this, I think we can solve a lot of problems in the future.
That's maybe a nice final quote. Otherwise, you have to add some more.
No.
No? Okay. So thanks again, Adrian Krischok, Thomas Domaschke, and Michael Kleinkes. That was a very, very intense and informative round. And well, to use the phrase you almost said, since you were talking of the Terminator, we'll be back at 2:30 p.m. German time, again with our second session here of the 5th day of our online summit. And in case you missed something, it's no problem. Just go to our online summit webpage and you can find all the sessions we had before, all 4 days. And of course, in the aftermath, this 5th day, you have the keynotes, you have the presentations in our live lounge, and of course the discussion panel in our networking lounge. So once again, thanks gentlemen,
Thank you.
and as I said, we'll be back. Have a great time.